This lesson is for matrices for BC Calculus after the AP test, and the first topic to introduce matrices is to remember how to solve systems of linear equations and to introduce some vocabulary that you may not be familiar with. So a system of linear equations, if it's a two-dimensional system, it might look something like, say, 2x minus 3y equals 7 and 5x plus 4y equals 12. And I just made that up, so we weren't going to try to solve it, but that's just to remind you what a system looks like. That is a two-dimensional system. The graphs of both equations are linear, and you would be trying to find the solution that's in common to them, which might be a graph that looks like this, where you would be finding the point of intersection. There's also three-dimensional systems that look like this, where there's variables x, y, and z, and the graph of each one of these is a plane in the three-dimensional coordinate system, and you might be looking for the common solution to all of these, which could be represented as a point or some of these other cases. So there's names for each of these cases. A system is considered consistent. It's a consistent system if there is at least one solution. A system is considered inconsistent if there are no solutions. And a system that is consistent, meaning that it has at least one solution, is considered independent if it has one solution, and dependent if it has infinite solutions. So you might be asked to classify which of these words apply to a system. And so in this case, a two-dimensional version with one solution or a three-dimensional version with one solution. The solution here is the point xy, and the solution here is the point xyz. And because it has at least one solution, I would say it's consistent. And because it has exactly one solution, I would say it's independent. So I can classify this with both words. It's a consistent, independent system. Both of these are. These are kind of two different examples of consistent, independent systems. All right, in this case, there's three different examples, and they are all examples of systems that have at least one solution, but in fact, infinite solutions. It's hard to see here, but the implication is if you know that this is the graph of a system, and it's showing you all the important features of the graph, then what happened is that the two lines that are involved in this system landed on top of each other, such that every point on the line is a solution to both equations in the system. So it would be like if these two were the exact same equation. And they're not usually given to you as 2x minus 3y equals 7 and 2x minus 3y equals 7, but some variation where the terms might be moved around or it might be multiplied by a constant. And so they don't appear to be the same function, but actually after you graph them or if you try to solve it, you get a situation that shows you that they are in fact the same line. So in a three-dimensional system that has an infinite number of answers or solutions, there could be a situation like this where all three planes have a line in common, or it might be that all three planes end up graphing to the same, all three equations end up graphing the same plane. So in either case, in either these cases or this two-dimensional one, we would call these consistent because there is at least one solution, but dependent because there are infinite solutions. And then the last case are the no solutions. There are no points that make both of these two equations true. So you can tell in the graph that the lines are parallel, and so there is no solution. And in this one, there are, like the dark blue plane and the pink plane here, they're intersecting in one line, but they don't have anything in common with the purple plane down here. So there, if you had three equations, there is no points, there's not even one single point that will make all three of these true simultaneously. And here's a different case of a three-dimensional system with no solutions. The planes might all be parallel to each other. So in all of these cases, there are no solution, and so we would call it an inconsistent system. And there is only one word that you would use to describe these. So this was one solution, infinite solutions, no solutions, and the words that classify them. All right, so I thought we've reviewed solving two-dimensional systems throughout the course at different times. So we're just going to go ahead and start with a three-dimensional system, and we're going to solve it without the use of matrices, and then we'll build up to using matrices to solve a system like this. So one thing I like to do is label the equations so that I can remember what it is that I was thinking would be a good idea to do these problems, to keep track of everything. Get some colors going here. I think that might help. So we're going to refer to this one as green, this one as blue, and the last one is red. So the idea to solve a three-dimensional system is you want to get the same variable to eliminate twice so that you end up with an equation with two equations with two variables instead of three equations with three variables. And you just want to look around to see if you think there's a particular set of numbers that might be easier to deal with than others. The way I chose to solve this system is I thought that the x's were good to work with. 1, 4, and 2 could all be manipulated into eliminating without too much effort. You could try it a different way if you want, and you should get the same solution. So my first suggestion was to take equation 1 and multiply it by -4. And if I do that, I will get -4x minus 4y minus plus 4z equals 4. And then I'm just going to rewrite the second equation. 4x minus 3y plus 2z equals 16. And then I'm going to add those two equations together, and I will get no x's, -7y plus 6z equals 20. And then I'm going to, so here I eliminate the x's, and now I want to eliminate the x's again. Here I used equations 1 and 2, so I can either use 1 and 3 or 2 and 3, and I'm thinking that 1 and 3 will be an easier choice because then I don't have to go use the 4 again. So I'm going to rewrite the third equation. And the third equation is 2x minus 2y minus 3z equals 5. Box this to help it stand out. And then I'm going to take the first equation and multiply it by -2 so that the first term x times negative 2 is negative 2x, and that's what I wanted to get, was the x's to eliminate. Then the next term will be negative 2y, and then positive 2z, and positive 2. Then add those together, the x's eliminate, I get negative 4y minus z equals 7. And now I'm going to take those two equations and use those to write a two-dimensional system to solve using our Algebra 1 skills. So negative 7y plus 6z equals 20, and negative 4y minus z equals 6. Now you could solve this by substitution or elimination. I'm going to keep going with elimination and take this equation here and probably eliminate the z's, because I can get that with one multiplication. So if I multiply everything in that equation by 6 and rewrite both of them, then I get negative 24y minus 6z equals 36. Uh-oh, I made a mistake somewhere. This is supposed to be a 7. Sorry about that. And then this is a 42. And then combine these, and negative 7y minus 20, and combined with a negative 24y is negative 31y. The z's cancel, and this adds up to 62. So y is equal to negative 2. So there's one solution. Now I can use either one of these equations up here to get what x is. What z is. So I'll say negative 4 times negative 2 minus z equals 7. So that's 8 minus z equals 7. Subtract 8 from both sides, and negative z equals negative 1. So z equals 1. And then now that I know y and z, I can use any of the original equations to solve for x. So I'll take the first one, x plus y minus z equals negative 1. And I don't know the x, but I know that the y is negative 2 and the z is 1. And so I get x minus 3 equals negative 1, so x equals 2. So that is the solution to the system. It's the one point that makes all three equations true. You could check it by substituting in x equals 2, y equals negative 2, and z equals 1. Here that would be 8 plus 6 is 14, plus 2 is 16. 2 times 2 is 4, plus 4 is 8, minus 3 is 5. And we know this one works because we got it with them, but we can double check. 2 minus 2 is 0, minus 1 equals negative 1. So if I were going to classify this system, I know that it is one of this situations where I get one answer. So I would say it is a consistent independent system. And we could write that here. Consistent independent. I'm going to pause and maybe just kind of do one page at a time from this packet, because this video is long enough. So we'll see how that goes. So I think you probably need to watch the next video before you move on to the lesson. Thanks.